You think you understand motion. You walk, you throw things, you drive cars. Motion is obvious, right? You move, things move, that's it. Wrong. Motion is one of the most misunderstood things in all of physics. Most people have completely backwards ideas about how things move. They think they understand it because they see it every day. But what they see and what's actually happening are two different things. Isaac Newton figured this out 300 years ago. He wrote down 3 laws, 3 simple statements about how things move. And these laws explain everything. Every motion you've ever seen, every motion that's ever happened anywhere in the universe. 3 laws, that's it. But here's the problem. The laws sound simple, but they're not obvious. In fact, they're deeply counterintuitive. They go against everything your everyday experience tells you. So let me explain them. Not with equations, not with formulas, with real examples. Things you see every day. And I'm going to show you why your intuition about motion is completely wrong. First law. Inertia, Newton's first law, says this. An object at rest stays at rest. An object in motion stays in motion at constant velocity, unless acted upon by an external force. That sounds simple. But think about what it's really saying. If something is moving, it keeps moving. Forever. At the same speed, in the same direction. Unless something stops it. Your brain rejects this immediately because that's not what you see. You roll a ball across the floor and it stops. You throw something and it falls down. Nothing keeps moving forever. Everything stops. So Newton must be wrong, right? No. You're forgetting something. Friction, air resistance, gravity. Those are forces. They're acting on the ball, the thrown object, everything. That's why they stop. Not because objects naturally slow down, but because forces are acting on them. Let me give you a real example. You're in a car. The car is moving at 60 miles per hour, steady speed, straight road. Now, close your eyes. Can you feel the motion? No, you can't feel anything. If you didn't look out the window, you wouldn't know you were moving. It feels exactly the same as sitting still. Why? Because you're moving at constant velocity, no acceleration. And without acceleration, there's no force. Your body can't detect constant motion. It can only detect changes in motion. This is Newton's first law in action. An object in motion stays in motion. You're moving at 60 miles per hour, and you keep moving at 60 miles per hour until something changes. Now the car hits the brakes. Suddenly, you lurch forward. Your body keeps trying to move at 60 miles per hour, but the car is slowing down. The seatbelt catches you. That's a force. The seatbelt is stopping your forward motion. Without the seatbelt, you'd keep going. You'd fly through the windshield. Not because the brakes made you move forward, but because you were already moving forward and the car stopped, but you didn't. This is why seatbelts save lives. Not because they hold you in place, but because they apply the force needed to change your motion to match the car's motion. Here's another example. You're standing in a bus. The bus isn't moving. Then it suddenly accelerates forward. What happens to you? You fall backward, or at least you stumble backward. Why? Your intuition says the acceleration pushed you backward. Wrong. The bus moved forward. You didn't. Your body wanted to stay at rest. The bus started moving, but you kept standing still. Relative to the ground, you didn't move. Relative to the bus, you moved backward. The floor of the bus pushed on your feet. That force accelerated your feet forward, but the rest of your body lagged behind. That's why you stumbled. Newton's first law is sometimes called the law of inertia. Inertia means resistance to changes in motion. Objects resist being sped up, slowed down, or turned. They want to keep doing what they're already doing. The more mass something has, the more inertia it has. A bowling ball has more inertia than a tennis ball. It's harder to get moving and harder to stop once it's moving. This is why big trucks take so long to stop. They have enormous inertia. The brakes apply force, but it takes time and distance to overcome all that inertia and bring the truck to a stop. And here's the really wild thing. In space, there's no friction, no air resistance. So if you throw something, it really does keep moving forever, at constant speed, in a straight line, forever. Unless it hits something or gets pulled by gravity. The Voyager spacecraft, launched in 1977, is still moving. It's billions of miles from Earth. And it's still going. Nobody's pushing it. Nobody's steering it. It's just coasting. Because in the vacuum of space, there's nothing to stop it. That's Newton's first law. Objects in motion stay in motion. It's not obvious because here on Earth, friction stops everything. But friction is a force. And the law says objects keep moving unless a force acts on them. Second law. Force and acceleration. Newton's second law is the most important one. It says force equals mass times acceleration. F equals ma. What does that mean in plain English? If you push on something, it accelerates. How much it accelerates depends on two things. How hard you push and how massive the thing is. Push harder, more acceleration. Push on something heavier, less acceleration. That's it. That's the whole law. But let's see what this means in real life. You're pushing a shopping cart. Empty cart. It's easy to push. It accelerates quickly. Now fill it with groceries. Same push, but now the cart barely moves. Why? More mass. Same force. More mass, less acceleration. F equals ma. Force stayed the same. Mass increased. So acceleration decreased. Here's another example. You drop two objects, a bowling ball and a feather. Which hits the ground first? In air, the bowling ball wins. But why? They're both being pulled by gravity. Same force? No, actually different forces. The bowling ball is heavier, so gravity pulls harder on it. But wait. The bowling ball also has more mass. More mass means more inertia, which means it should be harder to accelerate. These two effects exactly cancel out. Bigger gravitational force, bigger mass. They cancel, so everything falls at the same rate. This is why, in a vacuum, a feather and a bowling ball fall at the same speed. No air resistance, just gravity. And gravity accelerates everything equally. But in air, the feather floats down slowly. Why? Air resistance. The air pushes up on the feather. That's a force. It opposes gravity. So the net force is smaller, less force, less acceleration. The feather falls slowly. The bowling ball also experiences air resistance, but the bowling ball is heavy. Gravity pulls hard on it. The air resistance is relatively small, so the net force is still large. The ball accelerates quickly. F equals ma. Same equation. Different forces, different masses, different accelerations. Here's a more dramatic example. You're in a car crash. The car hits a wall at 30 miles per hour. The car stops in a fraction of a second, but your body is still moving at 30 miles per hour. To stop your body, a force is needed. F equals ma. Your body has mass. It needs to decelerate. Deceleration is negative acceleration. So force is needed. How much force? That depends on how quickly you stop. If you stop in a very short time, you need a very large force. If you stop over a longer time, you need less force. That's why cars have crumple zones. The front of the car is designed to crumple in a crash. This increases the time it takes to stop. Longer stopping time means less force. Less force means less injury. Airbags do the same thing. They increase the stopping time. Your head hits the airbag instead of the dashboard. The airbag compresses. That takes time. More time, less force, less injury. This is F equals ma in action. Same change in velocity, but different time. Different time means different acceleration. Different acceleration means different force. Here's another example. You're jumping. You push off the ground. Your legs apply force. That force accelerates you upward. The harder you push, the faster you accelerate, the higher you jump. But there's a limit. Your legs can only apply so much force, and your body has mass. F equals ma. Your maximum acceleration is limited by how much force your legs can produce divided by your body mass. This is why lighter people can jump higher. Same leg strength, less mass, more acceleration. Athletes understand this instinctively. Sprinters, jumpers, gymnasts, they all try to maximize their strength to weight ratio. More force, less mass, more acceleration. Third law, action and reaction. Newton's third law says, for every action there's an equal and opposite reaction. This is the most misunderstood law. People hear it and think they get it. But they don't. Here's what it means. When you push on something, it pushes back on you with exactly the same force, in the opposite direction, always. No exceptions. Every time you push, the thing you're pushing pushes back. Let me show you examples. You're standing on the ground. Gravity pulls you down. You're not falling. Why? Because the ground pushes up on you with exactly the same force as gravity pulls down. Those two forces are equal and opposite. They balance. So you don't accelerate. You just stand there. But here's the thing. The force of gravity pulling you down and the force of the ground pushing up, those are not action-reaction pairs. Those are two different forces acting on you. The action-reaction pair is this. Gravity pulls you down, and you pull the earth up with exactly the same force. You pull the earth up? Yes, you do. Newton's third law says so. The earth pulls on you, so you pull on the earth. Equally hard. But wait, if you pull the earth with the same force, why doesn't the earth move? It does move, but barely. Because the earth is massive. F equals ma. Same force, enormous mass, tiny acceleration. The earth accelerates toward you by an amount so small it's impossible to measure. Here's another example. You're swimming. You push the water backward. The water pushes you forward. Action and reaction. You push water, water pushes you. That's how you move. Rockets work the same way. The rocket pushes gas out the back. The gas pushes the rocket forward. Action and reaction. No air needed. No ground needed. Just push something one way and you go the other way. This is why rockets work in space. You don't need air to push against. You just need something to throw backward. The rocket throws gas backward at high speed. The gas pushes the rocket forward. Newton's third law. Here's another example. You punch a wall. Your fist applies force to the wall. The wall applies equal force back to your fist. Same force, opposite direction. Your fist hurts. Why? Because the wall pushed back. Hard. Same force you applied. But the wall doesn't break. It pushes back without moving much. This is why martial artists break boards. They apply enormous force very quickly. The board pushes back with the same force. But the board breaks before your hand does. Hopefully. Here's a tricky one. You're pulling a wagon. You pull the wagon forward. The wagon pulls you backward. Same force. So why do you move forward? Because there are other forces. Your feet push backward on the ground. The ground pushes forward on your feet. That's another action-reaction pair. The ground pushes you forward harder than the wagon pulls you backward. So you accelerate forward. Action-reaction pairs are always on different objects. You push the wagon pushes you. You push the ground pushes you. These are separate pairs. People get confused because they think action-reaction forces cancel out. They don't. They act on different objects. The force on the wagon and the force on you are different forces. They don't cancel. Here's one more. You're sitting in a chair. Gravity pulls you down. The chair pushes you up. Those forces balance. But where's the action-reaction pair? The earth pulls you down with gravity. You pull the earth up with gravity. That's one pair. The chair pushes up on you. You push down on the chair. That's another pair. 4 forces total. Two pairs. They're acting on different objects, so they don't all cancel. Putting it all together, these three laws explain every motion, every collision, every acceleration, every orbit, every rocket, every step you take. First law, objects keep doing what they're doing unless a force acts. This explains why you fly forward in a car crash, why spacecraft coast through space, why things don't just stop on their own. Second law, force equals mass times acceleration. This explains why heavy things are hard to push, why cars need crumple zones, why you can't jump as high when you're carrying weight. Third law. Every force has an equal and opposite reaction. This explains how you walk, how rockets work, why your hand hurts when you punch a wall. These aren't just rules, they're descriptions of how the universe actually works, and once you understand them, you see them everywhere. Every time you walk, you're pushing the earth backward. Every time you throw something, it's pushing back on you. Every time you accelerate, some force is causing it. And the beautiful thing is, these laws are exact. They're not approximations. They work perfectly, every time, everywhere. Newton figured this out 300 years ago. And we've been using these laws ever since, to design cars, to launch rockets, to understand the motion of planets. Three laws. They're profound in their implications because they tell us that motion isn't mysterious. It's not magic. It's predictable. It follows rules. And we know what those rules are. That's the power of physics. Not just understanding motion, but understanding that motion can be understood, that the universe follows laws, and we can figure out what those laws are. Newton's laws aren't just about motion, that proof that nature is comprehensible, that we can make sense of it, that the universe isn't chaos, it's order. Beautiful mathematical order. And that's worth understanding.